Good day, everyone. My name is Samuel Uzondu from the Malaria Research Unit, Department of Pharmaceutics, University of Nigeria, Nsukka. And I'm here at this prestigious international conference to present on my research titled Formulation, Characterization, Evaluation of WG19-Loaded / WG19 plus Chloroquine-Loaded solid lipid nanoparticles for the treatment of resistant malaria. Here are my outline. Malaria, as we all know, is a global health concern caused by a Plasmodium species transmitted by female Anopheles mosquito. According to the World Malaria Report 2020, Sub-Saharan Africa accounts for over 94% of the global malaria burden. My country, Nigeria, has the highest in-country malaria incidence of 27% in the world. With all these statistics, a major challenge to interventive efforts against malaria is the development of resistance by the parasites to anti-malarial drugs. Some is the development of or the emergence of artemisinin combination therapy resistance in the greater Mekong sub-region, comprising these countries Laos, Cambodia, Vietnam, Thailand, Myanmar, and Yunnan province in southern China. Now, what does resistance, do? Look at the class on the slide there. We have time to resistance onset profile of the antimalarial classes. You can see from the light purple portion, it shows the clinical lifespan of the various classes of antimalarial drugs. But the dark, the onset of the dark shade of purple shows you the onset of resistance to these drugs. You can see clearly as we go from one class to another, the clinical lifespan of these drugs are shortened by resistance. In Africa, WHO carried out a study from 2010 to 2018 on malaria prevalence, and they discovered that from 2010 to 2014, there was a decrease in malaria prevalence. But from 2015 upwards, there was a steady increase in malaria prevalence in Africa due to drug resistance. Now, let us look at the magnitude of this threat. On the slide there, we have the regions in the areas in the greater Mekong sub-region that have shown failures to ACT. The light shade of blue shown by Myanmar and China have reported failure to 1 ACT, while the moderate shade of blue represented by Laos and Thailand have reported failures to 2 or 3 ACTs. Then the darker shade of blue shown by Cambodia has reported failure to 4 ACTs. You can imagine when in a country, in a region, there is failure to 4 ACTs, and ACTs represents the drug, the first line of treatment of malaria, and also the drugs of last resort. And now we're having resistance to these classes of drugs. You can imagine what the impact will be globally. That will definitely be disastrous. So it's against this backdrop that this research was stimulated. We are looking for solutions. How do we solve this hydra-headed monster called anti-malarial drug resistance? That gave birth to this research. Of course, in Africa, we don't have a WHO documented failure to ACTs. What we have is chloroquine resistance. So in this research, we sought to combat chloroquine-resistant malaria by developing nanoformulations of WG19 and WG19 re-engineered chloroquine. That leads us to our research objectives. So what was our objectives? Number one was to evaluate the antimalarial efficacy of WG19-loaded and WG19 plus chloroquine-loaded solid lipid nanoparticles against NK65 and anchor strains of P. berghei. And secondly, to possibly establish a potential resistance reversing effect of chloroquine by WG19. And our research was anchored on this hypothesis that accumulation of this WG19-loaded and WG19 plus chloroquine-loaded SLNs would, inside the food vacuole of the parasite, would lead to cell death in both strains of the parasite. That our methodology was divided into 3 stages. The formulation stage, the SLNs were formulated using the modified hot homogenization process, and they were subsequently characterized for particle size, shape, intermediate efficiency, loading capacity, stability tests, physical and chemical. And then after we characterized, we took the optimized batch based on the particle size, based on encapsulation efficiency, based on the stability, and of course, finally, based on the in vitro release of the payloads. And then that optimized batch was used to do the in vivo studies. We used the batch to evaluate for acute toxicity tests using the LOX method, and of course did the in vivo studies using the curative, prophylactic, and suppressive protocol. These are the results of our research. The physical stability test showed that all the SLNs at a time of 30 days, 60 days, 90 and 120 days stored at various relative humidity of 25%, 75% at room temperature. They were all physically stable, as can be seen in the pictures there. There's no evidence of phase separation. And then the chemical stability test, we took a 5 ml aliquot of the SLNs and assayed for our payload. WOG19 in acidified acetone 1:4 absorbs at 380 nanometers. The lambda mass is at 380 nanometers. So at T30, we withdrew the 5 ml aliquot, T60, T90, T120. You can see the peaks at 380, showing that the payload is spread. They are chemically stable. Our acute toxicity test showed that at a dose of greater than or equal to 5,000 milligrams per kg of body weight, there were no macroscopic signs of toxicity in the mice groups, implying that WOG19-loaded and WOG19 plus chloroquine-loaded SLNs may be safe for possible human consumption. The PDIs. The result of the DSC, all the pure excipients there melted at they showed endothermic peaks at their respective melting point. This is for polazolam 407. The CS there is for compritol 88 which was the lipid matrix we used for our formulation. Then for the payload WOG19, each melting point is above 200 degrees centigrade, but the temperature range for which the DSC was carried out was between 30 to 100. So that's why there was no peak for WOG19. The same thing goes for between 80. Each melting point is below 30 degrees centigrade, and that's why there was no melting peak, and the formulation showed a completely amorphous, structure. Look at the DSC combined curve there. You can see that the lipid matrix showed a bimodal, peak, which implies that they had it comprised of at least 2 crystalline polymers. But when it was now, formulated with other excipients, you could see that there was a change in structure from a crystalline structure to an amorphous structure. And this is possible because the surfactant molecules intercalate between the lipid molecules, and this interaction helps to reduce the surface tension of the lipid, and also it also caused a change on the lipid structure from crystalline to amorphous, as seen in the FTIR study showed that all the excipients, the pure excipients gave their principal peaks, as according to literature. The arrow for the combination showed that the lipid matrix, the surfactants, and the payload were compatible. There was a broadband at 3347 per cm wave number, showing that there was hydrogen bonded interactions between the payload, the lipid matrix, and the surfactants. And this hydrogen interaction was very, very slight, as shown by the shift in their respective wave numbers. The result of the in vitro release studies showed that this is the in vitro release studies of our payload in phosphate buffer solution at pH 6.8 for the various parties of WOG19-loaded SLNs. You can see that in general the in vitro release is divided into 2 phases. It's generally biphasic, showing a drag initial phase and of course a spike at the 9th hour. This was carried out between 0 to 12 hours. So the reason why there was a drag in the first phase is because compritol 888 atol matrix does not break down. It maintains its structural integrity, and this means that the division of the payload is governed by the release of the payload is governed by the division of the payload across the lipid matrix into the release medium. But up until the 9th hour, there was a spike in the release of the payload. This may have been as a result of the partial breakdown in the lipid matrix that released the payload into the release medium. From the graph here, you can see that SC10 gave the best release. So it showed the highest correlation. There was a very high correlation across all the release models, showing the release of our payload has a multi-order behavior. It's quite complex. The in vivo studies in mice, we divided the mice into 5 groups. The placebo group, which was given the unloaded SLN, the formulation group, which was given the Wog19-loaded SLN, the combination group, which was given the WG plus chloroquine-loaded SLN, and then the pure chloroquine were the positive controls. You can see clearly from the anchor group that the placebo gave no activity, as shown by the increase in parastemia, which is understandable because there is no payload there. The formulation group gave a reduction in parastemia, but the combination group gave a greater reduction in parastemia. There's something interesting happened here. The positive control, there was no activity in chloroquine group. You can see that chloroquine here, there was an increase in parastemia. But when chloroquine was combined with Wog19 as shown in the combination group, there was a drastic reduction in parastemia, which suggests that Wog19 may have a potential resistance reversing effect on chloroquine. In the NK65 strain, which is a sensitive strain, the formulation group gave the best reduction in parastemia, followed by the combination group, and then followed by the positive control. And this reduction was significant, as shown by the p-value. P-value is p is less than 0.001. Model, the pure chloroquine gave the best prophylactic effect, as can be shown in the 2 slides there, followed by formulations. And of course, this is in agreement with literature concerning the behavior of chloroquine as a prophylactic agent. And this prophylactic action was significant, as shown by the p-value 0.034. The suppressive model, we had the combination gave the best suppressive effect in the anchor strain, while the chloroquine gave the best suppressive effect in this in the sensitive strain. And this suppressive action was significant with p equal to 0.003. In all, we use GAPA prison line to analyze our results, and we use the 2-way ANOVA repeated measures test to analyze these in vivo studies. From this research, we have established that Wog19-loaded SLNs have anti-malaria efficacy against both NK65 and anchor strains of P. berghei, and could be a potential lead in malaria treatment, resistant malaria treatment. Wog19 could also be a potential chloroquine resistance reversing agent, as we have seen in the slides for the curative model. Wog19 plus chloroquine-loaded SLNs has suppressive and curative anti-malaria efficacy against the anchor strain. Wog19-loaded and Wog19 plus chloroquine-loaded SLNs are potential game changers in the fight against resistant malaria parasites. These are my reference. Thank you for listening. All correspondences to samuel.uzondu@unn.edu.ng. Thank you for this opportunity.